Hello and welcome, coming to you once again, not quite live from One Take Studios, where today's topic is going to be special systems of equations, and my camera is going to continue to focus in and out until it settles down a bit. Alright, come on camera, you can do it. There we go. Alright, ladies and gentlemen, I'd like to start by looking at some vocabulary here. We have something the word is consistent. Alright, so what does it mean to have a consistent system of equations? A system of equations, if you remember, that just means that we've got more than one equation. Often we use two, but it could be more than two. And special means we got some kind of weird stuff going on here, some of the things that we don't see all the time. So consistent specifically says that this system has at least one answer. It could have one answer, it could have more than one answer, but as long as it has an answer, it is said to be consistent. Alright. Next word up then is inconsistent. Well, alright, so logically if consistent means it's got an answer, inconsistent means that it does not have an answer. Alright, that seems pretty straightforward as well. So along those lines, we've got some further breakdown actually for consistent. We have what are called independent systems, and right about there is where my one pen ran out. I started a different one, so I hope that doesn't bother you too badly. An independent system has exactly one solution. Notice the word exactly. No more, no less, just one. As opposed to, if a system is considered to be dependent, it has infinitely many solutions. In other words, not just one, it's got a whole bunch of solutions. And so both of these words right here, independent and dependent, are both used to describe, swinging up here, there we go, consistent systems of equations. So if we recap just based on vocabulary, if we're looking for a solution for a system of equations, it's possible that there could be one, and that would be a consistent system of equations. Almost seems like a tongue twister. That with inconsistent, it could be independent, or it could be dependent. Or it's possible that the system has no solution at all, in which case it is just inconsistent, and yay joy, there's no other words, it's just inconsistent, we can stop there. Alright, now what does that look like? Well, we spend a whole ton of time in math classes usually looking at how do I solve a system of equations, and we can do that through graphing, we can do that through substitution, we can do that through elimination. We have a whole bunch of options there. And we spend a ton of time looking for things that are not special cases, so today's just the weird stuff, alright? Just the weird stuff. Speaking of weird stuff, this first one is just a sketch to show vocabulary. If I'm looking at this, is this a special system? No, this one's just normal. The next two are going to be special. This is just normal. Alright, but these two lines, they cross. So this is a system of two equations. They are two linear equations. And to look at them graphically, I really like the graphic representation. It shows exactly where the solution is. That point right there, that's the solution. That point works on this line, and that point also works on this line. So just wanting to practice a new vocabulary here, what does that mean? If it's got one answer and one answer only, we would say that it is consistent, because it has at least one answer. There we go, I can spell. And because it has only one answer, we would also call it independent. Alright, let's move on to stranger things, shall we? Next up, if this is what it looks like, oops, can I get this? There we go. If this is what it looks like to have a solution, what does this mean? If the solution here is where the lines cross each other, where they intersect, and I'm looking here at this example of having parallel lines, if the lines are parallel, they have the exact same slope, where will they cross? Oh, that's right, they won't cross. So if I'm just looking at this, the visual for this is really nice. Again, if I'm going to use my vocabulary, this thing has no answer. Well, that means it's going to be inconsistent. And quite frankly, I don't have any other words to describe it. It's just inconsistent. And while that makes sense visually, what we struggle with sometimes is what does that look like algebraically? What if I didn't have this? What if I just had the equations and I said, hey, I'm going to work on solving this system? How would I know without the graph whether it had an answer or not, whether it's consistent or inconsistent? So what I have here is two equations, and based on the way they're set up, I'm going to do a couple different types of examples as far as style. This has the y by itself. And since it has the y by itself, that means that this equation is set up really nicely for substitution. Because this old chunk right here, that chunk equals y. So if I go back into the equation, I can take out the y, and I can substitute the negative 2x plus 1 in its place. So because the y is by itself, this is set up really beautifully for substitution. So I'm going to take my original equation, I'm going to write the 2x, I'm going to write the plus sign, but instead of the y, I'm going to put something that is equal to y. Instead of the y, I'm going to write negative 2x plus 1. All right, negative 2x plus 1. And going back to that first equation, I'm still going to put the equal sign, and I'm still going to put the negative 2. So I just rewrote the first equation, except in the first equation I took the y out, and I put the negative 2x plus 1 in its place. So what does it look like algebraically if we start solving? Well, 2x plus negative 2x. These are like terms, they're on the same side. I can just combine them. What is, if I put these combined together, what is 2x plus negative 2x? That's 2x minus 2x, that's 0. Ooh, that's gone. That's 0x, and then I've got plus 1 equals negative 2. But really, if you think about this, how often do we really write 0x? That's just kind of silly. So 0x, that's 0, plus 1 equals 2. What's 0 plus 1? 1. And therefore, 1 equals negative 2. Because we all know that to be totally correct, that 1 equals negative 2. Wait a minute. 1 does not equal negative 2. That's problematic. And so what we see here is variables dropped out, and what we're left with is a false statement. We've actually seen this before without systems of equations, just regular old equations if we're solving. If all of our variables drop out and we are left with a false statement, there is no solution. And so algebraically, that's what it looks like for a system as well. Not just one equation, but two. When I start the solving process, if all of the variables drop out and I'm left with a false statement, I know this thing has no solution. Here's what that looks like graphically, and here's what that looks like algebraically. So I don't necessarily have to graph it in order to figure out that this is an inconsistent system, something with no solution. All right, one example left. One left to go. What if I've got this? All right, so if you're looking at this going, what is she doing? Why is there only one line? Because this one had 2 lines and this one had 2 lines. I would like to say that this one also has 2 lines. Why can't you see them both? Oh, in this case, the 2 lines are in the exact same place. I've got one line right over top of the other. So there are 2 lines, but one is covering the other. They're in the exact same spot. Well, okay, so let's think about what that means as far as our vocabulary. If the solution is where they intersect each other, where they touch, these 2 lines touch in one place. Where do these lines touch? They touch here and here and here and here and here and here and here. They touch at every single point on this line. And since this line goes on forever and ever and ever, this is what it looks like to graph infinitely many solutions. So there is an answer, at least one answer, so we're going to call it consistent. That's still true. But we're also going to call it dependent, because it has not just one solution where they touch, but every single point along the line they're touching each other. So this has infinitely many. This thing goes on forever. You do want to be careful. You don't want to call this all real solutions or all real numbers or anything like that, because while this line goes on forever and there are points that they are touching forever and ever and ever, what if I pick this point right here? This point right here? Right there. Boom, right there. Is that point on that line? No. Is that point a solution to the system? No. So every point that's off in space someplace else is not a solution. So there's lots of numbers out there that are not part of the solution, but yet somehow there's still infinitely many because the line goes on forever. So all of these points count as answers, but not points out here anywhere. All right, so hopefully that makes some sense. So the next question then comes again, what would that look like algebraically? Again, if I didn't graph this, if I was just looking at it algebraically, how would I know if I was running into this circumstance, if I can't see it happening? Well, all right, so the last one I set up, I said this one was really nice for substitution because I got that y by itself. It's really easy for me to plug it in. Well, what is this one set up pretty nicely for? X's are lined up, y's are lined up, my constants are lined up. This is set up pretty well to do something along the lines of elimination, where I can add the 2 lines together and make something drop out. All right, so what might I do for something like that? Let's say that I'd like to make the x's drop out. So this one here has a 3x already. So what if I took that top equation and said, I'm going to take that top equation, I'm going to multiply it times a negative 3. So x minus y equals 2. In parentheses, we're going to multiply that whole thing by negative 3. Why did I pick negative 3? Well, let's think about this for a second. Negative 3 times x is negative 3x. Negative 3 times negative y is plus 3y. And negative 3 times 2 is negative 6. I want to set up this circumstance where I've got something that drops out. That means I need opposites. So if this one says 3x, I want this one to say negative 3x. And that's why I chose a negative 3. I'm creating a situation, setting it up on purpose so that these two guys, when I put them together, are going to cancel out. So I didn't touch this equation. 3x minus 3y equals 6. I did alter this equation, so here's the new version. Negative 3x plus 3y equals negative 6. And now I'm set up to do a really nice elimination problem where I'm just going to line these two puppies up. There we go. And add these two equations together. So what is 3x plus negative 3x? 0x. Woohoo! What is negative 3y plus 3y? Wait a minute. Wait a minute. I wanted those to drop out. What's happening here? These are also dropping out? Negative 3y plus 3y? So now I've got 0 y's as well? Well, this is ridiculous. 6 minus 6? What's 6 plus negative? That's also 0. Everything is gone. I mean, look at this. This is 0x, that's 0. 0y, that's 0. So 0 plus 0 equals 0. Well, I guess good news at least. The last time I checked, 0 does actually equal 0. So great, yay for us. What does that mean? Well, do a comparison. Last time everything dropped out and the numbers made a false statement. No solution. Here, again the variables drop out, but what we're left with is a true statement. And so very similar to what happens when we solve regular equations, when we're not talking about systems, when we're left with something true. Something true, that means that we've got a bunch of answers. Or in this case specifically, we have infinitely many. Infinite, I can spell. There we go. Infinitely many solutions. Alright, so we spent a ton of time, whoops, there we go, solving these guys. So I did not focus much time at all about solving with one system today, with one solution for my system today. But these are my special cases saying, all right, if I'm looking at these, there's my spacing. If I'm looking at these, it's possible to not have an answer. And algebraically, here's what would happen. The variables would all kind of undo each other, fall apart, leaving you something false, no solution. And here's what this special case would look like if they are the exact same line. If they're the exact same line, everything drops out because they've got the same slope, they've got the same y-intercept. Everything's going to drop out, leaving you with a true statement, and this is what infinitely many solutions would look like. All right, so you've got to keep your eyes open, got to keep your brain functioning as far as what you might be looking at, but keep in mind that these are all the possibilities. These are all the things that could happen. And even if you don't have a system of lines, even if you've got a system of parabolas or circles or anything else, all of this stuff is still true. Either they cross each other, or they don't, or they're identical. That's it. Okay? All right, so keep your eyes open and have some fun with that. Good luck.